My boss comes into my lab, hands me a bottle of compound A and a bottle of compound B, and tells me I have to make compound C from them. What other reagents will I have to buy in order to achieve this synthesis? All right, so looking at this, we have an alkyl halide, a secondary bromide, and we have an aldehyde. And from those two things, we're being asked to make compound C. So you note that on our alkyl halide, we have two phenyl groups on the carbon that's attached to the bromine, and here we have two phenyl groups on the carbon that's part of our alkene. All right, over here we have a methyl and a hydrogen on our aldehyde, and not surprisingly, on the other carbon of our alkene, we have a methyl and a hydrogen. All right, so in order to form an alkene between these two carbons, we want to do Wittig chemistry. All right, so we need to form a phosphonium halide from our alkyl halide, and we need to deprotonate that alpha to the phosphorylated carbon to form our ylide. All right, so we're going to need triphenylphosphine, and we're going to need N-butylithium. That's what I'm most concerned about. If you also said ether because it's the solvent, that's great, but if you didn't, that's also fine. This next question is, why should I go to my boss and tell him that I'm going to use compounds D and E instead? Right, so this isn't a trick question. It's telling you that it's best to use compounds D and E instead. So the explanation for this is that it all depends on how easy it is to form the phosphonium halide salt. So how easy is it for a phosphine nucleophile to displace the halogen of your alkyl halide? All right, so compound A is a secondary halide. Compound E is a primary halide. This goes back to SN2 chemistry. A primary leaving group is going to react faster than a secondary leaving group in an SN2-like reaction, which is what a phosphine displacement of a halogen is. All right, so it's because E is going to react better with phosphorus. Okay, so now we're ready for the last part of the question, which is a synthesis question. All right, so let me just get this set up real fast. All right, so provide the reaction sequence for the whole synthesis of C from D and E, and the mechanism for the sequence's final reaction. Right, this sequence has multiple steps. Bonus points if you draw the final reaction's transition state. All right, so this is a Wittig reaction. The first step is going to be the displacement of the halogen. All right, so here we have our bromoethane. All right, we're going to treat this with triphenylphosphine. All right, the lone pair on phosphine is going to displace the bromide. All right, and we're going to end up with a phosphonium. And that will have the countercharge of the bromide. All right, so there are hydrogens on this carbon. And now that there is a positively charged phosphorus attached, these are going to become very acidic, or at least more so. So N-butylithium looks like this. Very, very basic. This will come in, deprotonate there, and that will form our ylide. All right, so here's our ylide. We have the negatively charged carbon and the positively charged phosphorus. And so now what we need is our carbonyl, which in this case is a ketone. Right, we're using species D and E to make our desired product. All right, and so this is a concerted reaction. You have the negative charge of the ylide attacking the partially positive carbon of the carbonyl. That breaks the pi bond, which attacks phosphorus. All right, and that's going to give us our oxaphosphetane. So here's our oxaphosphetane. The red is from the ketone, the blue is from the ylide, and the black lines are the new sigma bonds. This is a four-membered ring. It's not happy, it's very strained. And so This will collapse. We will form a phosphorus-oxygen double bond while forming our alkene bond here. Okay, it doesn't matter which one of these bonds you draw going to the alkene and which you draw going to the phosphorus-oxygen bond, as long as you draw each one being formed. All right, and at that point we have our final product, and that is that. Now the bonus question is the transition state for the Wittig reaction, which is, so I'll try to keep the color coding here. So we have our phosphorus from our ylide. Okay, the bond between phosphorus and carbon is not changing in the transition state. That's staying a sigma bond. All right, but you're forming a bond between that carbon and the carbonyl carbon of the ketone. All right, that the pi bond of that carbonyl is being broken, and you're forming a new oxygen phosphorus bond. So that is a dotted line between oxygen and phosphorus. So again, you're just drawing in the bonds that are forming and breaking as dotted lines in the transition state. Don't forget to make sure that everything else that's connected to these carbons is drawn. So the methyl group on the ylide carbon, you can either draw the hydrogen or leave that implied. That's fine. Okay, if you'd also like to make it official, give it brackets with the double cross so that it's very apparent that it is the transition state. And that's the end of the first page.